Chapter 7, we will be learning the different methods of solving systems of linear equations. Before we look at the first method, we will first learn how to write a system of linear equations in matrix form. Any system of linear equations can be written as a matrix called the augmented matrix by simply writing the coefficients and constants that appear in the equation. Example, if you have this system of linear equations with three unknowns x, y, and z, the augmented matrix is given by this. The first column contains the coefficients of x, the second column contains the coefficients of y, the third column contains the coefficients of z, and the last column contains the constants. So for the first equation, x plus 2y minus 4z equal to 5, this represents the first row of the augmented matrix with entries 1, 2, negative 4, and 5. For the second equation, we have 2, 1, negative 6, and 8. For the last equation, we have the coefficients 4, negative 1, negative 12, and the constant 13. Another illustration is this. We have three equations and three unknowns. The augmented matrix is given by this matrix. For the first equation, we have 1, 2, negative 4, 5. For the second equation, we have 0, negative 3, 2, and negative 2. For the last equation, we have 0, 0, negative 2, and negative 1. So now we will be learning how to solve a given system of linear equations by Gaussian elimination. First, we will understand a matrix that is in row echelon form. So a matrix is said to be in REF or row echelon form if the following conditions are satisfied. First, the first non-zero number in each row is 1, and that is called the leading entry. Next is the leading entry in each row is to the right of the leading entry in the row immediately above it. And lastly, all rows consisting entirely of zeros are at the bottom of the matrix. Here is an illustration of a matrix in row echelon form or REF. The leading entry for every row is 1. The leading entry of a row is to the right of the leading entry of the row immediately above it. Now, how do we transform a matrix into REF or into row echelon form? So we can do any of the following row operations. First is we can add a multiple of one row to another. Next is we can multiply a row by a non-zero constant. And lastly, we can interchange two rows. So in symbols, we have the following. This one means that we change the ith row by adding k to the jth row to that row I, and then put the result back in row I. This symbol describes a row that is multiplied by a constant k, and the last one represents an operation by interchanging the ith and the jth rows. So how do we systematically put a matrix in REF? So first is we start by obtaining a 1 in the top left corner. Then obtain the zeros exactly below that leading entry. Next is we obtain a leading 1 in the next row and then obtain zeros below that 1. And lastly, we continue this process until you arrive at a matrix in REF. So using the row echelon form or the REF to solve a system of linear equations is called Gaussian elimination. How do we do the Gaussian elimination? Here is the following steps that will help you do the Gaussian elimination. First, we express the system of linear equation in augmented matrix. Then we transform that matrix into REF. And lastly, we solve the system by back substitution. And how do we do back substitution? We write the new system of the equation that corresponds to the REF of the augmented matrix and then solve the system. So here's an example. Let us solve the following system of linear equations using Gaussian elimination. First, we represent this system of linear equation in matrix form or in augmented matrix. So first, let's look at the first equation. We have the coefficients 4, positive 8, negative 4, and the constant 4. For the second equation, 3, 8, 5, negative 11. And the last equation, we have the coefficients negative 2, 1, 12, and negative 17. Now, let us look at the top left entry in the augmented matrix. It's 4. So our goal here is to obtain a 1 in this spot. So to do that, we perform an elementary row operation. Let us multiply row 1 by 1/4. So we get 1, 2, negative 1, and 1. Simply multiplying every entry in the first row by 1/4. The rest of the rows, we simply copy them. Next goal is to obtain zeros below the leading entry 1. So we have to transform 3 to 0 and negative 2 to 0. So to do that, what we do is we multiply by negative 3 to R1 and add that to R2, and that will be our new R2. So doing that, by the way, we simply copy the first row. And then for the second row, after applying this operation, we get a 0 here. Then we have negative 3 times 2 plus 8, so that's a 2. The negative 3 times negative 1 is positive 3 plus 5, we get an 8. Negative 3 times 1 is negative 3 plus negative 11, it's negative 14. Now for negative 2 to become 0, what we can do is multiply row 1 by 2 and add that to row 3. So we have here 2 times 1 is 2 plus negative 2 is 0. Then next entry, we have 2 times 2 is 4 plus 1, so we have a 5. And doing the same thing to the next entry, so 2 times negative 1 is negative 2 plus 12 is positive 10. And lastly, we have negative 15. After that, our next goal is to make this entry here 1. So to do that, what we can do is perform another row operation. We multiply row 2 by 1/2. So we simply copy row 1 and row 3, and then the second row is transformed into 0. And then this is 2 times 1/2 is 1, and then 8 times 1/2 is 4. Negative 14 times 1/2 is negative 7. After that, what we want to do is to make the entry below 1 0. So to do that, we can multiply negative 5 to row number 2 and then add to R3. So we copy rows 1 and 2. For the first entry of the third row, we have negative 5 times 0, that's 0 plus 0, that's why I still have a 0 here. Now, negative 5 times 1 is negative 5 plus 5, that's why we'll get a 0. Next is we have negative 5 times 4 is negative 20 plus 10, so that's a negative 10. And lastly, we have negative 5 times negative 7 is positive 35 plus negative 15 is positive 20. And then, finally, we have to make this entry negative 10. The leading entry of every row must be 1. So to do that, we multiply the third row by negative 1/10. Doing that, and simply copying the first and the second rows, we get a 0 here, and a positive 1, and negative 1 times 20 is negative 2. So with this augmented matrix, we can express this into a system of linear equation whose solution is exactly the solution of the original system that we looked at. So for the first row, this corresponds to the equation x plus 2y minus z equal to 1. For the second row, this column is for variable y, so we have y plus 4z equal to negative 7. And lastly, we have z equal to negative 2. Now, solving for the values of x, y, and z, looking at the system, we already have a value for z. Now, solving for the value of y, we can substitute this value of z to the second equation. So we have y plus 4 times negative 2 equal to negative 7. Solving for y, we get a 1. And finally, to solve for the value of x, we simply substitute the values of y and z that we got to the first equation. So we have x plus 2 times positive 1 minus z is negative 2 equal to 1. So solving for x, the value of x is negative 3. So the solution is the ordered triple negative 3, 1, negative 2.